Our next lesson here today is a continuation of Solutions 1. This lesson will deal with concentration. And in this lesson, we are going to look at a few different things. We're going to look at solutions, some details about what the parts of solutions are. And then we're going to look at three different types of concentration. We're going to look at percent by mass, molarity, and molality. Each one of these three things is a method or a measurement of concentration, and so we're going to look at those guys right there, how to calculate them. So first thing, we defined a solution before. We talked about that solutions were mixtures where basically we have one substance that's dispersed through another, and the substance that is dispersed basically has particle sizes that are less than a nanometer, and as a result, basically that solution in this case is homogeneous. That is, that the particles are uniform throughout it. And we talked about some other things that deal with that. But right now, we need to do a little bit of definition about the parts of a solution. A solution, as we're talking about here, is made up of a solute dissolved into a solvent. And so the solute, the first part we're sort of dealing with here, is the material which is dissolved. So if we were talking about salt water, the solute in salt water would be salt, because it is the material which is dissolved, and salt is dissolved in salt water. It's the one that actually is dispersed throughout the other one. The solvent is the dissolving material. That is, in salt water, it would be the water. So it would be the material which the solute is dispersed into. So that's the solvent here. The solution, on the other hand, is the combination of the two. So it's the combination of the solute and the solvent. So in salt water, the solution is the salt water. So in a sense, if we know the mass of the solute and we know the mass of the solvent, if we want to find the mass of the solution, we'd simply add these two guys up, and that would equal our mass of our solution over here. And so those are your three parts here. Solute, solvent, solution. And if we want to figure out the concentration of the solution, and we say concentration, basically what we're dealing with is this issue here. We can have a solution which has different amounts of solute with respect to the solvents, different proportions there. You can imagine, if we're talking about salt water, is that we could have, a gallon of water and we could put 1 grain of salt in it. Do we have a saltwater solution in that case? Yes, we do. But that's a very different saltwater solution to one in which you were to, say, dip a gallon of ocean water out. Which has much more salt, much more solute in this case, mixed into the solvent than does the one where you simply have a grain of salt in the whole solution. And so we need a way of basically being able to describe how much solute there is in a solution proportionate to the whole solution as a whole. Sort of in this case, how salty the water is, or in the case of something like an acid, what the concentration of that acid is, how strong it is. And so if we want to talk about the concentration of a solution, so this is what we're dealing with here. The concentration of a solution is described always in terms of the amount of solute per either solution or solvent. So it'll either be amount of solute per solution or it'll be amount of solute per solvent. But when we say amount, that's a pretty general term. Amount could be volume, it could be mass, could be number of moles, number of atoms. And so as a result, there really isn't one good way of measuring concentration. There are actually probably a good 24 or so that are used in various ways. We are going to focus in this class on 3 different ways of measuring concentration. And the first one is the one that's actually probably most commonly used in sort of everyday life. And that is called percent by mass. And so let's take a look at this. Percent by mass, or sometimes called the mass percentage, is one way of measuring concentration. And the equation is basically this: that percent by mass is equal to the number of grams of solute divided by the number of grams of solution, and then times 100. We have that times 100 out there is basically because this is a percent. And so we need to basically multiply by 100 to get into a percent form. So let's take a look at an example here. We have 14.5 grams of KCl was dissolved. Let's see, get rid of that was. That's gone now. 14.5 grams KCl is dissolved in water to produce a 210 gram KCl solution. What is the percent by mass? So we know this. We know that percent by mass is going to be equal to the number of grams of solute. And so in this case, what's our solute? Remember that the solute is the material which is dissolved, not the one that does the dissolving, the one that is dissolved. In that case, it's going to be the KCl, the potassium chloride. And so that means, how much do I have of that? Well, we're looking for, as it says, grams of solute, and so I have 14.5 grams. of KCl over the number of grams of solution. My solution here is water because it says dissolved in water. And so actually, I'm not even paying attention here, am I? So gram solution, not the grams of solvent. The water is the solvent, not the solution. And so I'm looking for the number of grams of solution here. Number of grams of solution. And so it tells me the grams of solution, KCl solution right here, is 210 grams. And so we have 210 grams of solution here, and then I've got to multiply that by 100 to get it into the right form here. Doing so with my grams of solute divided by grams of solution, that if you take out your calculators, then you can sort of set it up and you say 14.5 divided by 210, and then you have to multiply that times 100 to get into percent, and so I get 6.90 is what I get out of this, so 6.90%. In this case, look at significant figures. I start off with 14.5, that has 3 sig figs. 210 has 2, so my answer should have 2. So my final answer is this is a 6.9% KCl solution, potassium chloride solution. As I said, this method is the one that is probably the most commonly used in everyday sort of life. You will sometimes see this when someone talks about something being, say, a 10% saline solution. Basically, what they're just saying here is that's the percent by mass. That this is 10% by mass saline or salt solution. And so this is how you'd work out percent by mass problem. So let's take a look a little farther here. Oops. So let's try another couple cases here. So 45 grams of sugar is dissolved in 100 grams of water. What is the concentration in percent by mass? So we're looking for percent by mass again. Percent by mass, remember, is going to be equal to the number of grams of the solute. And so the solute here is sugar. And how many grams do I have? I have 45. So I have 45 grams of sugar divided by the mass of the solution. And so I'm told that I have 100 grams of water. Same problem I messed up on last time here. Water is not the solution, water is the solvent. To find the total solution, I'd have to say, add up the solute, sugar, and add up the solution, water. And so I'd say 45 plus 100 gives me 145. And so that's going to be the mass of my solution here. And then times 100 to get into percent. And so doing so, we go ahead and we take our guy, we say 45, then divided by 145, and then times 100. And so I get 31.03, 03%. Significant figure-wise, 45 grams, that's spelled out, so it's infinite significant figures. 100 grams of water, that's only at 1 sig fig, and so we'll round this to 1 significant figure. And so our answer is that this is a 30% sugar solution. And that's how you work that out. Let's try another one. How much barium sulfate must be added to 300 grams of water to produce a 45% barium sulfate solution? So we're going to use the same. It says that it's a 45% barium sulfate solution, and so we know the percent by mass in this case, 45. This is equal to the number of grams of solute. Do we know that? Well, it says how much barium sulfate. Barium sulfates are solute, so we don't know what that is, so we're going to call that just X up here, divided by the mass of the solution. Well, we have 300 grams, but that's 300 grams of water. That's the solvent, not the solution. And so to do this, we're going to have to say 300 plus X, because we have, in order to find the mass of the solution, we've got to add the mass of the solute, which is X, plus the mass of the solvent, which is 300 grams of water. And so this is what we have to start with. And then, of course, times 100, right? Times 100 up here. And so in order to get this to work, we're going to have to sort of solve here. We want to divide both sides by 100 first. That'll cancel out the 100 on over here on the right. I don't know what I'm thinking here today. So we're going to end up, we do that, we get 0.45. We're then going to want to multiply up the 300 plus X like that, and this is going to equal X, just like that. So then going ahead a little farther here, we take out our calculators. Let's distribute the 0.45 through. And so when we do that, we get 0.45 times 300. And so I get 135 for that. So we get 135 plus 0.45x equals X. And so we want to subtract off 45 tenths from 45 tenths x from both sides, so minus 0.45x. And so when we do that, we get 135 is equal to 0.55x, because just x minus 0.45x equals 0.55x. Divide both sides by 0.55. Doing that, that's going to cancel out on one side our 0.55s right over here, and that should let us go ahead and figure this out. So we'd say 135 divided by 0.55, and I get 245.55. And so in this case right here, if we wanted to produce a 45% barium sulfate solution, I would need 45, in this case 0.5 grams. Significant figure-wise, 300 has one significant figure, 45 has two, so my answer should have one significant figure, which arounded is 200 grams of barium sulfate would be my final answer. So that's how you would use percent by mass to work out some basic calculations. Let's take a look and keep going here. Let's look at our next method of finding concentration. And this next method is not as commonly used in sort of everyday work, but is the most common one used in chemistry, and that's molarity. The most common method for measuring solution concentration chemistry is molarity. The symbol for molarity is capital M, and it is important that this is a capital M, as we'll find out in a second. There's something else that's lowercase m. Typically is if you're describing something with respect to molarity, you'd say that if you have like your molarity is 7, you'd say it's a 7 molar solution, and you'd write it out sort of like this. You'd say 7 capital M. That's how you show 7 molar solution. Has a molarity of 7. And so that's sort of just formatting on that. The definition of molarity is equal to the number of the moles of solute divided by liters of solution. And the reason why molarity is so useful is that if you are reacting something with a solution, or you're reacting two solutions together, whenever you're doing that, you're going to want to do stoichiometry, for one thing. And since you're doing stoichiometry, you always have to go to moles first. And well, if you have, to start with, moles of solute, then the solute's what really does the reacting. You don't have to do another conversion. If we had something in terms of gram solute, we'd have to, one, go from our concentration to find the number of grams, and we had to convert from grams to moles. Using molarity, once you found basically what your molarity is, it's relatively easy to go ahead and figure out how many moles you've got. It's already in moles. The second reason why that molarity is so commonly used is that typically when you're measuring liquids, you don't measure them by mass. And so if I have some solution, if I want to measure it out, typically I'm going to pour it into a graduated cylinder or some other volume measuring device, and I'm going to measure it in liters. And so by using molarity, if you're trying to figure out how many moles you have, all you really have to do is just measure out your amount of volume in liters, and then it's pretty easy just to plug it into this equation here, and then that'll tell you what the molarity is. Or if you know the molarity, and you know how many liters you have, it's very easy to figure out how many moles you have. And so this is basically the reason why molarity is such a nice unit of concentration to use. So let's start off by seeing how this works here. So we have an example. Half a mole of sodium chloride is dissolved to produce 250 milliliters of solution. What is the molarity? So in this case right here, we're looking for molarity. Molarity is equal to moles of solute. And so in this case, how much solute? What's the solute here? It's sodium chloride dissolved into presumably water in this case. And so sodium chloride is going to be basically what our solute is, and how much we have. We have half a mole. So we have 0.5 moles of that guy right there, divided by the number of liters of solution. We're told we have 250 milliliters. 250 milliliters, remember milli is thousandth. We move the decimal place over 3 spots, and so this is going to be 0.250 milliliters, or liters, not milliliters, liters right there. Okay, and then once we've done that, that should tell us the molarity. And so we take the calculator, 0.5 divided by 0.25, and in this case you get 2, which should be fairly obvious there. And so in this case, this is a 2 molar solution. Significant figures, half a mole has infinite significant figures, 250 milliliters has 2. Our answer should have 2. So actually this is one of these rare cases where we actually have to increase the number of decimals we have on here. And so our final answer is this is a 2 molar sodium chloride solution. And so that's how you basically work out molarity. So continuing here, Let's work out a couple more examples of how molarity would function. So 4.5 liters of a 1.3 molar HCl, hydrochloric acid solution, contains how many grams of HCl? So first thing we know here is that we have the concentration. It's 1.3 molar. And so we're going to say 1.3 molar solution. This is equal to the number of moles of solute. And the solute here is the hydrochloric acid. And how many grams of that do we have? Well, that's what we don't know. It says how many of these. So that's going to be X. We don't know how many moles we have. Divided by the number of liters of solution, and it tells us we have 4.5 liters of solution. So we have 4.5 liters right there. And so to solve this, let's go ahead and get X. We want to multiply 4.5 on both sides. And so we get 1.3 times 4.5. And in doing that, I get 5.85. And so I have 5.85 moles of hydrochloric acid, HCl. But the question asked me how many grams. And so because it asks how many grams, I've now got to go take this 5.85 and do a conversion with it. And so I'm going to put it in my table, 5.85 moles of HCl. I'm going to put it in my table here. I want to cancel moles. I want to go to grams. And so you're going to need the periodic table for this, because anytime we convert from moles to grams, we use the periodic table. And for hydrochloric acid, hydrogen has a mass of 1.01. Chlorine has a mass of 35.45. So we end up with 36.46. 36.46 is what we get for our number of grams in a mole. So 36.46 is grams in 1 mole. And so moles HCl cancel. We go to grams. So we'd simply take our 5.85 times 36.46. And in doing that, I get 213.291. Our answer, since things have two significant figures on both sides here, then we're going to end up with 210 grams of HCl, hydrochloric acid, would be our final answer. So if I have 4.5 liters of 1.3 molar solution, I had to add, or I have inside of that, 210 grams of hydrochloric acid. So look at another one. How many liters of a 0.45 molar barium chloride solution could be made with 1.1 moles of barium chloride? So in this case right here, I know the molarity to start with. I have a 0.45 molar solution, 0.45 molar. And so in this case right here, I know that's going to be moles of solute. My solute here is barium chloride. How many moles do I have? I have 1.1 moles. So I say 1.1 moles of barium chloride on top. On bottom should be liters of solution. And do I know what that is? Nope, it asks me how many liters of solution. And so that's going to be my X right here. So I have X liters down here. And so to solve this, I'm going to multiply X up on both sides to start with. And then as soon as you do that, that nicely cancels off our X's down there. And so we are left with 0.45X equals 1.1. Want to divide both sides by 0.45. That's a 5 down there. And so in doing so, if you put in the calculator, 1.1 divided by 0.45, that gives you 2.444, repeating. Okay? Significant figure-wise here is that, taking a look, we have how many liters of 0.45 molar? That's got two significant figures. Or made with 1.1 moles, that's got two significant figures. So our answer should be rounded to 2 sig figs. And so in this case right here, we would get 2.4 liters of our solution would be our final answer. That's how you'd go about using molarity. So that being said, let's take a look at our final measure of concentration. That's molality. You may have noticed that unfortunately, these last two things have some very, very similar names. Molarity and molality. You've got to be a little careful. They just happen to have similar names. There actually is a third form of concentration called molality, which we're not going to talk about. So you have, molarity, molality, and molality. But molality is the one we're dealing with here. This is often confused with molarity because it sounds similar. Molality, which notice the symbol for that, lowercase m. That's why we got to be careful of our capitals and lowercases. Capital M is molarity, lowercase is molality. So molality is another measurement of concentration. The definition is this. Molality is equal to the number of moles of solute over kilograms of solvent. Note that this one is a little bit different than our previous two. previous to, in that previously we always had some amount of solute divided by some amount of solution. For percent by mass, it was grams of solution. For molarity, it was liters solution. But this time we have kilograms of solvent. So molality is used a lot of cases whenever you are either you know how much water you're adding, you really don't care about how much total solution you get, all you know is what you're adding there. It's also oftentimes used in reaction kinematics, which we'll talk about later on in the year, and it's used in, we'll use later in this unit here, in cases where you're trying to figure out how solutions change what the boiling and freezing points are of liquids. And so this is molality. So we'll work out an example here. 300 grams of sulfuric acid, H2SO4, is added to 300 grams of water. What is the molality? So in this case right here, we know molality is equal to mole solute. So our solute here is the sulfuric acid, H2SO4. We need moles of that though. We're given grams, 300 grams. We're going to have to convert that. And so what you want to do first is set up our table. So we have 300 grams of H2SO4. And we want to go ahead and try converting that over. We want to get rid of grams. We want to go to moles of this right here. And so once again, break out your periodic table. We have, in this case, 2 times hydrogen, which is 1.01, plus 1 sulfur. Looking at the periodic table, we see the sulfur is 32.07, so plus 32.07, plus SO4, so we have 4 oxygens, so plus 4 times 16. And so in this case, I get 98.09, and so 98.09 grams in 1 mole. And so doing this, we'd say 300, which is the number of grams we start with, divided by 98.09. And so I get 3.058 moles. So I know I have 3.058 moles of H2SO4. No rounding yet because we're not to our final answer. We want to find our molality. Well, molality, we said, is equal to the number of moles of solute, which we just found, 3.058 moles, divided by the number of kilograms of solvent. Solvent would be water in this case. How many kilograms do we have? Don't know, but we have 300 grams. Easy to convert. Remember, once again, is their kilo to grams is a conversion above 1,000, and so 300 grams would be 0.3 kilograms. So we have 0.3 kilograms here. So to find the molality, we take our 3.058 divided by 0.3, and I get 10.195. Significant figures. In this case right here is I've got 300 of each one, so that has 1 sig fig, that has 1 sig fig, and so our final answer is going to have 1 sig fig, and so in this case right here, our final answer is just 10. So we have a 10 molal solution. And so this is where I have to be a little bit careful here. Once again, we're talking about molarity. It's called a 10 mole. It would be called a molar solution. With molality, it's called a molal solution. But in this case, I have a 10 molal H2SO4 solution. Would be my final answer. So that's how you do a basic molality problem. Onward we go. Do a couple more examples on molality. Oops, that says molarity at the top. That should be molality at the top. Let's see if we can change that. Molality. Okay. How many grams of NaCl, sodium chloride, must be added to 400 grams water to produce a 4.5 molal solution? And so in this case right here is that we know we have a 4.5 molal solution. A molality, remember, is equal to the number of moles of the solute. Solute here is NaCl. We don't know that, so that'll be X over the number of kilograms of solution with kilograms of solute. Kilograms of solute. The solute here is water, and so we have 400 grams. That would be 0.4 kilograms there. And so to solve for X, we're simply going to multiply up 0.4 times 4.5. So 0.4 times 4.5 gives us 1.8. So I know I have 1.8 moles of NaCl. Question asks for, though, how many grams. So I'm going to want to set this up in my table. So 1.8 moles of NaCl. I want to get rid of moles. I want to go to grams. And so in this case right here, we go back to our periodic table. We look at sodium Na, it's 22.99. Plus chlorine, which is 35.45. And so when you add those two up, we get 58.44. 58.44, and that's in 1 mole. So 58.44 times 1.8 divided by 1 gives us 105.92. 105.92 grams of NaCl. Significant figure-wise, taking a look at this, we have a 4.5 molar solution, that's 2 sig figs. 400 grams has 1 sig fig, and so this would simply round to one significant figure. 105.92 just rounds to 100. So I have 100 grams of NaCl would be my final answer here. The number of grams of NaCl needed to create 400 grams of, added to 400 grams of water to produce a 4.5 molal solution. One last one here. If we have 1.4 moles of KCl, they're added to water, the resulting solution is found to have a mass of 750 grams. What is the solution's molality? And so in this case right here is that we're looking for molality. And so we'll go ahead and set this up, and so we say that molality is equal to the number of moles of your solute. Solute here is KCl. We know we have 1.4 moles of that, divided by the number of kilograms of solute. Sorry, kilograms of solvent. And so in this case right here, we know that the solution has a mass of 750. We do not know what our water has a mass of. So we're going to have to figure this out, because what we know is the solution is 750. And so if we could subtract off the solution, the amount, the mass of KCl, then we know how much water we had left. But the problem is right now we're in moles of KCl, so our first step here, and this one is about as complex as they get, is we're going to start off with 1.4 moles of KCl. We want to go ahead and we want to convert that from moles to grams of KCl. And so taking a look at our periodic table here, because that's how we convert from moles to grams, we see potassium has a mass of 39.1. So we take 39.1 plus chlorine, which we look up and we see is 35.45. That gives us 74.55. So 74.55 grams in 1 mole. 74.55 times 1.4 gives us 104.37. So we have 104.37 grams of the potassium chloride. Now, since we have 750 grams of the solution, when we have 104.37 grams of potassium chloride, if we subtract those two, 750 minus 104.37, then that gives us 645.63. So 645.63 is the number of grams of water. So we need kilograms of water, though, and so to go from grams to kilograms, we once again move the decimal place over 3 spots. And so in this case right here, I'm going to get 0.645 kilograms of my solvent. And so to find the molality, I take my number of moles of KCl, 1.4, divided by my number of kilograms of solvent, which is 0.64563 if you want to take it out the whole way. And so I get in this case that we have a 2.168 molal solution. 2.168 molal solution. Significant figure-wise is that we have 1.4 moles KCl, that's 2 sig figs. I have 750 grams, that's 2 sig figs. So I know that my 1.4 on top has 2. For my guy on the bottom, the 0.645, is that in order to do that, I had to find the number of grams of the KCl first, and that should have 2 significant figures. So that means this guy right here is rounded, has 2 sig figs right here. So the 1 and the 0 are significant right there for each one. Then when I subtract that from 750, that's the tens place. This guy right here is the tens place. That means my answer should be around the tens place. So 6 and the 4 are significant. That means this guy should have 2 significant figures. That means I've got 2 for both of them. My answer should have 2. So that means my final answer here would be 2.2. And so I have a 2.2 molal solution for my final answer here. And so the solution's molality, I have a 2.2 molal potassium chloride solution.